So moving on, the contents of today's presentation. So first I'll give you a brief introduction of what is considered to be a tall building. Then we'll go into what is the need for having tall buildings. Then we'll look at some of the factors that are affecting tall buildings. And after that, I will just quickly explain some of the conceptual considerations we make in terms of structural design of tall buildings. And the next topic will be wind and wind loading, wind tunnel testing. Now, during the presentation, I'll try to explain why wind loading is very critical for tall building design. And then I'll quickly go through the design process that we do in overall design of a tall building. And then I'll also just touch upon some career path in terms of structural engineering field and what job opportunities would be available for structural design engineers. So firstly, so what is defined as a tall building? Now we have seen a lot of buildings with various heights across India and across the overall the world as well. Now there is no particular definition of what is a tall building. It is very subjective. It could be subjective in terms of the country we live in. For example, what is considered tall building in India may not be a tall building in US. But however, CTBUH, which is a Council of Tall Building and Urban Habitat, they have come up with a criteria for having some sort of an measurement of a tall building. So if you see the image on the right, you can clearly see that a tall building is considered anything within greater than 50 meters, but within 300 meters of height. And if it is greater than 300 meters, it is considered to be a super tall building. And if it is greater than 600 meters, it is considered to be a mega tall building. Now, the reason is also the design process slightly varies across this, which I'll try to address during this presentation. Now, overall, currently there are around 170 super tall buildings around the world, and there is around 3 completed mega tall buildings. Now, why I say completed is there are still some buildings which are being constructed, which is more than 600 meters. However, these are not yet completed. Now, going down to the next one. So, why do we need a tall building? What is the driving factor for requiring a tall building in any country or in any place? If you see the image at the right side, I hope many of you would already identify the building. This is Burj Khalifa, the tallest building in the world. It stands at around 800 plus meters. Now, I will try to explain why Burj Khalifa was required or why they considered Burj Khalifa to be constructed, and thus address why generally tall buildings are required for any country or any place. So first point is demand due to high concentration of population density. Now, Burj Khalifa is located in Dubai, as many of you would know. And post 2000, there was a large influx of people coming into Dubai because of the economic development here. And with more people coming in and concentrated in the main city, they considered to have one tall, super tall structure which will accommodate more people. So it generally an accommodation for more number of people within a given area of land, which is quite obvious. So that is one reason they go for super tall buildings. And in countries like China, where the population density is very high, in cities like Hong Kong, etc., you will see a lot of tall buildings to just accommodate the number of people coming into the city. So second point is requirements for proximity of business. Now, when you have a business, you always like to be in the center of the city because that's where you get all the resources. So with more businesses requiring to be in the center of the city, you obviously need more office spaces, which means more tall buildings. And the third point is to create a distinctive landmark. Now we know that Burj Khalifa is in the UAE, so that itself becomes a landmark. The building in itself acts as a landmark for the whole city and country. And also, if you see all the buildings around Burj Khalifa in this particular picture itself, there is a lot of activity happening around Burj Khalifa. It's almost a community there, which is developed once Burj Khalifa was constructed. So that is also one reason. And it also becomes a high value area when you say that you are staying or you have an office next to Burj Khalifa. It adds some value to the land around it as well. The fourth reason is prestige simple. Of course, you stand out in the world as a country with the tallest building. And it also acts as a tourist attraction. And then the final point I put in here is called vertical cities. Now, this is a concept which is coming up over the world now, which basically means you have one building in which you will have your residence, you will have your office, you will have retail spaces for all the shopping requirements, you will have a lot of restaurants, and you may even have a recreational area within the same building. So you basically don't have to go out of a tower to get anything. All the requirements are within one building, and this is only achieved if that building is going to be a tall building. So these are some of the reasons why they go for tall buildings around the world. Now, Burj Khalifa is only an example. These points will apply to maybe Petronas Towers in Malaysia and a lot of other buildings. So generally, these are the factors which affect. Now, the next point. So if there are so many advantages to have a tall building, why don't everybody go for tall buildings? Obviously, there should be some challenges in constructing a tall building or designing a tall building. So the factors which affect the tall buildings, I've tried to list out some of the factors which is generally considered when somebody decides to construct a tall building. The first one is, of course, economic feasibility of the project. So building a tall building itself is very costly. So the owner or the client, whoever wants to construct it, will try to see if he gets a benefit out of building this tower. There's no point building a tall building at a location where he's not going to get any revenue. So that is one reason. The second one is availability of materials. I will explain later. You will need higher strength concrete and higher strength reinforcement to provide the structural elements of a tall building. So these are not available in all countries. So that is one reason. Same with the level of construction technology. If you see the picture on the right, that is from one of the towers in China, you can see cranes located at probably it's around 500 meters above the ground. So you need a certain technology to be able to construct tall buildings itself. And the fourth one is also, it's not only about structural design for a tall building. You also need to have good lift, which is the vertical transportations. So you should have high-speed lifts to transport people across this building. You should have required fire protection services to ensure that the building is not burnt and affects people. You should have a good facade technology, and you should also have proper mechanical and electrical services. So all of these coming together becomes factors for deciding if a tall building can be constructed or not. The fifth point is availability of skilled expertise, and then also the feasibility of foundation system. Now you are putting so much load on the soil should be able to transfer these loads safely. So that also is a factor in considering whether to build a tall building or not. Let's move into some of the design considerations. So what I thought first is to explain what are the components within a tall building. So if you see the image on the right side, these are all floor plans of various different high-rise buildings. The names of the buildings are there. For example, this is the floor plan of Taipei Tower. Then you have International Finance Center and etc. Now, if you look closely, you have certain components which are repeated across these layouts. So the first one is the internal structural core, which is this one. If you can see my mouse pointer. So this forms the structural core of a tall building. Now, these cores provide various utilities. One is this act as the typical service area, which includes all the lift, the stairs, the MEP areas. MEP is mechanical, electrical, and plumbing. So all the service requirements are accommodated within this structural core. And it also acts as the main structural stability system of the building, which I'll explain shortly. The next one is the usable area around the structural core. So if you see all these colored areas around the core, this will typically be the space that is rented out in terms of office or in terms of residential or in terms of any use that is required to be. So this area basically becomes the sellable space for the owner. The next one is the external support systems. Now, I told you already that this internal core becomes the main structural system. Similarly, we also have a row of columns on the external side of the building. So these two together form the main structural system of any building. And this will typically be across most of the towers, if you see. So everywhere you will have an internal structural system and then an external structural system. And finally, we also have the facade. So the facade is basically, if most of you should know, but anyway, it is basically the external covering of any building. Now, if you see typically glazing, which is glass, is used as an external covering in many tall buildings, or it can be cladding. Cladding is any other material like aluminum or etc., which are used to cover the face of the building. Let us move into some more detailed structural discussions now. So to design any building, short building, tall building, or any building, the first consideration that we need to understand is what are the loads acting on the building. So this is the same for tall building design as well. So the first thing that we as engineers try to understand is what the building is to be designed for. That is, what is the loads acting on the building. So there are two types of loads generally acting on any structure. The first one is gravity loads, which is downward force acting axially on the members of the building, as you see in the diagram here. This gravity load generally includes self-weight of the structure, whether it's your concrete or steel or any structural element that you're using. It also includes the weight of the other materials, such as your tiles, your facade, your blockwork, etc. So basically, it includes all the loads that are permanently acting on the structure. And also it includes live loads. Now, live loads means the loads which are not permanent, but which are transient in nature, such as the weight of the people coming into the building or the weight of the vehicles coming into the building in case of a parking layout. So how do we define what is the live loads? These are generally defined by codes. So there are certain values that need to be followed in terms of what is the usage area. For example, if there's a parking area, the code will tell you, okay, use 3 or 4 kilonewton per meter square as the load wherever there is parking. So all these together form the gravity loads acting downwards. And the next set of loads is the lateral loads. Now, lateral means horizontal. So whatever loads that are going to act horizontal to the building will be called as lateral loads. Generally, there are two major lateral loads that is to be considered. One is the wind load and the other is the earthquake load or seismic load, whatever we call it. So these, like I said, act in the horizontal direction. The second point is this depends on the size and shape of the building and the geographical location. For example, if you have a wind load, the wind forces are going to be different in different locations. Like if you see within India itself, the wind force may be different down south and it may be different up north. So it depends on the location of the building, and it also depends on the size and shape of the building, because the wind load depends on how much area is exposed to it. We'll see that shortly also as we go forward. Now, how do we define these values? As a design engineer, generally we are guided by codes to use maximum probable values. So there are estimates of what will be the wind load acting in a certain geographical area. And then we have certain guidelines which we follow to use the wind load on a building. Similarly, for the seismic loads or earthquake loads, as most of you know, we have a seismic zone map for India, which divides the different regions into zone 1 to zone 5, depending on the earthquake probability in that area. And based on that, we calculate the seismic loads acting on the building. Now, there are two types of gravity loads, like I said, gravity and lateral loads. How do we combine these loads? So there will be a situation where your gravity loads are acting and simultaneously there's a wind load acting on the building. So there are load combinations within the codes which tell you how much of gravity load you need to consider at the same time when a certain percentage of wind load is acting on the building. Now, I'm not going into details of these, but generally you can understand there are load combinations to be used. Now, okay, we understand what is the loads acting on a building. So let us try to understand how the building is going to respond to this load. I'm going to compare the building to a cantilever beam here. Now, as you can understand, any building, short building or tall building, is basically a cantilever structure with the base to be considered as fixed and the top end the free end of the cantilever, similar to what you see here for the cantilever beam. There's one fixed end and one free end. Now, when there is a gravity load acting, it's very simple. It's axial load going down into the structure. But when there is a wind load acting, this is where the difference between a short building design and a tall building design is primarily. So when there is a wind load acting on any structure, if it is a short building, I'll just go towards the cantilever beam to explain this. So I put in the formula for deflection of a cantilever beam. Now there is a certain load acting on a beam. The deflection of the beam depends on the load acting as well as the length of the beam. Now, in our case, The length of the beam is basically the height of the building. Now, provided there's a constant wind load acting on a building, in case of a short building, the deflection at the top will be much lesser than a tall building because of this factor to the power 4. So this is one basic difference between a short building design and a tall building design. The taller you go with a building, the more deflection you will see at the top of the building. This deflection is what will govern the design of a tall building. So what are the parameters generally that governs in terms of a deflection? So when I say deflection, what happens is you have a wind load acting on a building. The building starts to sway to the right. Of course, it is elastic in nature, so it wants to come back to its position, and then it will try to sway back to the left and right. So it acts like a pendulum, tries to come back to its position. Now, in this action, there are 4 elements which are very critical, which is time period, displacement, frequency, and acceleration. Now, you would have heard all of these topics in general physics in the design of a simple pendulum. And this is exactly what we'll be trying to do in the design of a tall building as well. So our main point as a designer is to restrict this displacement at the top due to various reasons, which I will explain shortly as well. So how do we restrict this displacement at the top? Now, again, going back to this deflection formula, the load and the height or the length of the beam is directly proportional to the deflection. But the stiffness, which is the EI factor, E is your modulus of elasticity of the material used, either concrete or steel, and I is the moment of inertia of your structural system. Now, this E into I is called stiffness factor of a building. So the higher the stiffness factor, the lower the deflection of the building. So in order to reduce the deflection at the top of your building, we will have to increase the stiffness of this building. So that is what we will be trying to do in a tall building design. In a short building design, the stiffness may not be much critical because the displacement is not too much. But in a tall building design, the stiffness becomes very critical because you want to restrict the displacement at the top. So this is in brief the difference between tall building and short building design. Now let's move on to the limit states of the design. Like I said, there are 2 limit states. One is the strength design and the stiffness design. Generally in short buildings, strength governs. In the tall buildings, stiffness also plays a critical part. So how do you address the strength limit state, which is basically ultimate limit state? Now, again, if you see the image on the right, this is an ideal behavior of a tall building, which again is a cantilever. So you have a gravity load acting, which here is represented as P, and then you have a lateral load, which is represented as V. Now, when these loads are acting, you will have a deflection here, and then which is what we are trying to restrict to certain limits. And then you will also have bending moment in the building, you will have shear in the building, and you will have axial force in the building. Now, we as a designer, we will be trying to design a structure which is equilibrium in nature. So basically, you will have to make sure that your building is able to resist all the forces acting on it. So this is what we'll be trying to do in a tall building design in terms of strength. Now, in terms of stiffness, it's again all about the deflection. Like I said already, as the height of the building increases, your deflection also increases. So our stiffness has to increase in order to control this deflection. Now, what is the reason to control this deflection? Why do we worry so much about a building deflecting at the top? There are various reasons to this. Some of them I've listed here. It needs to be maintained in order to ensure proper functioning of elevators. Now, in a tall building, there is elevators definitely. If a building is deflecting too much, your elevators require to be straight. But if your building is not straight, the elevators will not function properly. So that is the first reason. The second reason is to avoid damage to the glazing. Now, there is glazing on the outer face of your building. If your building is going to deflect too much, then there's going to be additional stress on these glazings. And that's when you see glass pieces falling off a building because it is moving too much, which the glass design is not supposed to take. So that is one reason. And also you will see a lot of cracks in your partition walls, which is your block work, which again is not designed to take too much of a deflection. The other reason is also it causes discomfort to occupants. Now, just suppose there is a 300-meter tall building. You have a family renting the flat at the topmost level. If there is too much deflection, now when I say too much deflection, this may not be visible to the naked eye, but to a person who's staying at the top of a building, he can feel this movement of the building. He feels in the form of giddiness or in the form of other discomfort to him. Now, you don't want a building to sway too much because you will not be able to rent that space if somebody is not comfortable living there. So that is also one of the main reasons why we have to restrict this deflection in a tall building design. Now, how do we restrict the deflection? I keep saying, okay, restrict it. But to what do we restrict it? This is based on some parameters which are set by codes. So there are different codes across different countries, which give you certain values to be followed in terms of design of this displacement. So there are three factors generally. One is overall displacement. The next is interstory drift. And the third is the human comfort criteria. So I'll just explain quickly each of these. The first one is overall displacement is nothing but the amount of displacement you see at the top of a building from the base. So that gives you the total deflection of the building. The interstory drift is the same thing, but the measurement is from one story to other story. So whatever the deflection is happening in a certain level from the lower slab to the higher slab is called as interstory drift. Now, there are certain values I mentioned that needs to be followed in terms of drift. So one of the factors I have taken from American code, so it requires the drift to be within the height over 400 to height over 600. So when you say overall displacement, if you have a 300-meter tall building, your displacement at the top should not exceed 300 meters divided by 400. So whatever is the meters you get, that should be your maximum deflection of the building. If it is beyond that, you need to put in some measures to control this deflection. So that is how we address the overall displacement and the interstory drift. Now, in terms of human comfort criteria, which is the third one that I was mentioning, this one is generally, there is no particular standard covering this human comfort criteria in general, but there are certain accepted values. And how do we measure this is based on the acceleration. So this goes back to the four parameters that I told you before: time period, displacement, frequency, and acceleration. So in this case, your acceleration of the building is critical to determine how much of a comfort a human will feel at the top of the building. So there are agreed values, which again is set by CTBEH, which gives you limiting acceleration of the building. Now, how we measure the acceleration, I'll come to you in a short time. I'll just explain to you. But just understand that in order to define the human comfort criteria, you measure the acceleration of a building and limit it to certain agreed values.